Okay, thank you. It's really an honor to be here, and I guess to represent the entirety of the experimental community. It is a bit ironic for those that know me, because I'm certainly also a fan of math, but I'm going to try to do my best to provide some counterpoint. So with further ado, we saw earlier this nice picture from exactly 100 years ago of the eclipse that was so crucial to studying, to confirming Einstein's theory of general relativity. So I just thought I would show it again larger, though it was a special moment to see the actual original earlier. This debate that goes back and forth, I was kind of surprised that these terms weren't brought up before. I'm not a philosopher or historian of science, but there's this sort of duality between two approaches, which are roughly empiricism, which is this very experimentally driven view, which Newton was certainly a fan of, versus rationalism, which was more this idea that through, more through mathematics and our intuition, that we could somehow intuit what the underlying laws of nature are. And of course, both of them have quite a few marks up their sleeve, which they can say they've had successes. But this is essentially the duality that we're discussing today. I'm just going to start off with a few quotes. So Murray Gell-Mann, who unfortunately passed away just recently, was of course someone who was very influential in terms of the introduction of mathematical thinking that ended up there was skepticism at first, but then very much bore fruit in terms of a whole series of experiments. So here there's a long quote, but this one part you see this unreasonable effectiveness of certain parts of mathematics in describing physical reality. So he's certainly on this kind of rationalist side. And then here's a quote from Richard Feynman, who's talking about it doesn't really matter how beautiful your guess is. He also goes on to say, or how smart you are, but if your theory disagrees with experiment, it's wrong. And so this is, I think, we could talk about it more, but I don't really think anyone in this room is going to disagree that if you do an experiment that you have a prediction from a theory that doesn't agree with experiment, and once everyone does the appropriate checks, that they're going to still argue that that theory is the right description of reality. I think what we're after is much more of a nuanced interplay between the role of this kind of mathematical directed approach to physics versus a more empirical approach. So I'm going to try to tell some stories and give some other points of view. So as an experimentalist, probably one of my major areas of expertise is really along the lines of the statistical data analysis. And so George Box is a famous statistician, and he has this pithy quote of all models are wrong, but some are useful. And it's interesting because when he's saying this, he's really thinking of sort of statistical models, but you might as well think of physical models as well. And then there's this follow-up quote from Sir David Cox, who's also a statistician. And I love this part that's buried inside. It says, the idea that a complex physical, biological, or sociological system can be exactly described by a few formula is patently absurd. And which is, it's interesting because from if you were with a group of statisticians, this would not be a controversial type of statement. Either of these, everyone would agree with. And so in some sense, this corner of the academic universe, there are several people that are after a theory of everything and are hoping that we will come up with some specific formulas that are going to really describe what's going on. One thing that I'll come back to is that, of course, things get really messy when you start talking about real experiments. So oftentimes we have to try to idealize situations and work very hard to come with very clean experiments or very idealized circumstances because the everyday world that we interact with involves many interacting systems, is very complicated and very hard to figure out. But now also with the era of deep learning and machine learning and artificial intelligence and all of these things, there's a group of this community that's also going even further and making even bolder claims. So here's a spin on Box's quote that says, all models are wrong, and increasingly you can succeed without them. And what he's basically saying, and you can tell from the diagrams on his shirt and stuff, is a very computer science-oriented, data-forward sort of attitude, and it's gone so far as to what I would consider, kind of rubbish statements that are saying that essentially with the deluge of data and big data and computing and all these things that the scientific method is basically obsolete and theory is dead. And this is a very strong statement, and also one that I also very much don't agree with, even though I'm very active in this sphere of data science and machine learning and things like that. So now I want to go through kind of a specific grounded example of the interplay between theory and experiment and pick out some places where it was great, places where it failed, and places where I think the whole narrative about how theoretical physics and experimental physics is kind of not being framed correctly, or not how I would frame it. So my grounded example is literally found on the ground. Here is a rock, a geode, and this kind of geode, if you will fluoresce or phosphoresce, and it was studying these because these have uranium salts in them, and studying these kinds of minerals and things like that, that radioactivity was discovered. And shortly after that, in the quest to try to understand radioactivity and then starting to categorize the different types, quantum mechanics was developed along the way, and very quickly, then relativity and field theory. We heard about Maxwell. All of these ideas were being shoved together into what was cleverly named relativistic quantum field theory. And so these ideas, when applied to try to understand radioactivity, went pretty well. So in particular, Fermi in 1933 was proposing some theory for what's going on with radioactive decay. And one thing that I like is that these kinds of simple diagrams is really kind of how is a totally reasonable way to think of it, and this is the kind of what would later become sort of Feynman diagrams. So you have, in this case, a neutron that's decaying into these, proton, an electron, and a neutrino. And so this theory was very successful in describing radioactivity at the energy scales that we were probing it, but there was not really an experimental problem, there was a mathematical problem. And that it was basically that if you tried to use this theory and extrapolate it to high energy scales, it started to develop some mathematical sickness. In particular, it gave you these kind of rubbish answers where you had probabilities that were larger than 1. Sometimes that's referred to as unitarity violation, or the idea that the theory is not renormalizable. And so this was, at that time, a mathematical problem. It wasn't that it was in tension with the experiment. And the solution at that point was basically to hypothesize that maybe there's a force-carrying particle, a W boson. Okay. So I'm giving kind of a lowbrow version of the particle physics here, so I hope my esteemed theorist friends will forgive me. But here's a paper in 1982 that was sort of describing the evolution of this idea. People had been looking for these intermediate force-carrying bosons and not seen them. And at that point, the standard model had been developed, and there was really this idea that we should go after it and see if we can confirm this theory. And you see that, again, this idea that that it's constructed presuming that the elementary particle interactions can be described by some renormalizable field theory. So this quest was, convincing to the community, and we built a, several kilometer long ring with accelerators to go try to test this theory and see if we could discover the W and the Z bosons. And so here's a picture of the SPS when it was reconfigured to collide protons and antiprotons. And lo and behold, just shortly thereafter, we were able to discover the W and the Z boson. So here's an example of a Z boson being produced and decaying into 2 particles flying out of a detector. This is in the 80s, so the computer graphics aren't so great. I love that this graphic is still very preliminary. But okay, so we've discovered the Z. This was a huge success. Okay, so why am I telling you this story? Partially is because the same line of logic is going to be repeated again. So if we think of this is an energy scale going from chemical reactions to essentially like the mass of a proton. Way over here on the right is the Planck scale. That's where we were thinking about string theory and effects of quantum gravity. And so in this more intermediate range, we were expecting some sort of phenomena to happen. And so why did people expect there was going to be some sort of phenomena? That's basically using the same idea. If you imagine these W bosons running into each other, the theory had, again, a kind of internal inconsistency or a sickness. And that could be solved by several mechanisms, but one of them was the idea of a Higgs boson. So, and that would only work if the Higgs wasn't too heavy. So that's kind of the location of the star. So again, people were like, okay, let's go look for this Higgs boson. We have an idea of what energy it's going to take. Here's a picture of Peter Higgs with a blackboard describing his theory and the kind of iconic picture of the Higgs potential. And in that same 1982 review, there's also a little blurb about the Higgs boson, and it talks about how many physicists find the Higgs field inelegant. And one of the reasons that's mentioned is this idea that radiative corrections to the Higgs boson are significant, okay? And I'm not going to go into a lot of detail on this, but I want to say a little bit because it again kind of underscores the relationship between mathematics and physics and how it convinces the field to go and do these experiments. Okay, so there's a quantity that you can measure. You can take a particle called a muon, and it has a spin, and it also has a little magnetic field around it. And there's a relationship between the magnetic field of that particle and its spin, and that's called the gyromagnetic ratio. And in normal quantum mechanics, that number would just be 2, just exactly 2. But with the advent of quantum field theory, this 2 number gets a small correction, and it's related to these kinds of Feynman diagrams drawings. And so when you go and you compute it, you get some number that's a small correction to 2, and people got very good at calculating more and more corrections to get a very precise prediction for what this number is. And what's interesting is that people also came up with not just beautiful theory, but beautiful experiments, really clever experiments to be able to measure this quantity, this fundamental quantity of nature, incredibly precisely. And so now the theory and the experiment are both at this ridiculous level of precision, which is something like hitting a hole-in-one from New York to China. So this is a tour de force for both the experimental and the theoretical community, and they're coming together. And currently there's even a little bit of tension, which people are excited about, but overall the agreement is very good. So why am I telling you this story? Partially it's because if we use the same logic and we apply it to the Higgs, something happens. The Higgs, if you think about the mass of the Higgs, it also receives quantum corrections. And here are some diagrams that are associated to these quantum corrections. But instead of it going from 2 to 2 plus a little tiny bit, the corrections are now huge, like very, very big. And so as just a quick analogy for this, I like to think of sort of the budget. So you have 2 types of contributions. You have positive contributions, which you can think of as income. You have negative contributions, which you can think of as spending. And then you have a surplus, which is like the physical Higgs boson mass. And so the Higgs boson mass that we will now have measured, and we're expecting already at that time, is so small compared to the scale of the other 2 that it's confusing. It's like saying that the budget is balanced to better than a penny, and there's no particular reason or coordination between spending and taxation, right? So that would be very hard to understand. It would be unnatural, right? So. And this analogy kind of continues with ideas of renormalization and things, but I won't go into that. So if you wanted to understand how is it that the budget could be balanced to better than a penny, you would probably think there's a reason. Like, oh, maybe they're not totally, spending and taxation are not totally independent. Maybe someone came to Washington with an amendment and said, we need a balanced budget, we need expenditures to equal revenue, and you just didn't know that. But once you found that out, oh, okay, of course everything makes sense, that's why the budget's balanced, because that's kind of built in by design. So the analogy of that in physics is something called supersymmetry. And this isn't the only motivation for supersymmetry, but in my story, it's one aspect of it that makes sense. And in supersymmetry, one thing that happens is that there's a pairing between one kind of particle called fermions and another kind of particle called bosons. And those come in with positive and negative signs, sort of like spending and taxation. And that in supersymmetry is the reason why the Higgs boson mass would be not some huge number. Okay. So this was roughly the analogy, and this is sometimes called naturalness. Supersymmetry is coming up with a mechanism to explain why the Higgs boson mass is sort of naturally some small number. So that's great, and it motivated people, but some grumpy experimentalists like Carlo Rubbia, who had just found the W and Z, had this great line. He says, and now for every particle we have, there's another particle that we don't have, and of course we're supposed to find them. So this is like the onus is on the experimentalists to go find these crazy particles that the theorists had predicted, right? So this then kind of led to the next era of experiments. So this is now a 17-mile ring in Geneva, Switzerland, the LEP tunnel. And in the United States, there was the Tevatron collider, which is much smaller, colliding a different type of particle, but even higher energies. And so these experiments were not only looking for the Higgs, they were also looking for evidence of supersymmetry. And we have not yet found supersymmetry. And in what is a kind of painful science journalism example, there is this article in the New York Times saying 315 physicists report failure in search for supersymmetry, as if it's our fault that supersymmetry is not there, right? So, so that's something to keep in mind, that these, we learned something about nature. We learned that nature does not choose supersymmetry at this energy scale. So, that was a positive contribution. Of course, from the point of view of everyone thought it was going to happen, and it wasn't, that's not what happened, then you could cast it as a failure if you want. But that's, that's not the way that I would report it. And certainly as an experimentalist, this is not how I would describe it. There's the line right below it says the negative results illustrate the risks of big science and often sparse pickings. And I think that part is definitely true. These are expensive experiments, it's big science, and we don't discover particles like every week. We discover them very rarely because we're really probing the very most fundamental aspects of nature. So let me go back to this about, this is our energy scale. We've been doing some experiments probing around this star, and basically the idea at this point is we're going to need a bigger boat. We need more energy if we're going to conclusively say something about that energy scale, and that's where the Large Hadron Collider comes in. So, so at this point we're off to try to discover supersymmetry, the Higgs boson. This is what the Large Hadron Collider looks like. This is the ATLAS experiment. There's another experiment called CMS, is similarly large and complicated. And at the time, during the decades between the discovery of the top quark and the W boson to building this experiment, we hadn't really discovered anything else. There wasn't really another experiment in town that was pushing the frontier. And during that time, a group of model building theorists came up with all sorts of ideas. And so here are all sorts of examples. There's a zoo of different theories and different models that we were going to be testing. And most of these were motivated, again, by this issue of naturalness. So they weren't, so it was an exciting time. And at the time, I would have discussions with Nima and company. And the problem was, when the new physics starts pouring out of the LHC, how are we going to figure out what it is? How are we going to figure out which one of these is the right story? And everyone was very excited, and really the whole community kind of bought that this was, it was very likely that this was one of these scenarios was going to happen. What we didn't expect was that right after we turned it on, that something would explode. Okay, so one of the magnets exploded, and it took about a year and change to fix it. And here's another little side vignette parable: is that during this time, some theorist friends of mine were saying, well, at the previous experiments, there was something that the experimentalists missed. And so here's an example. I'm not going to go through it. There's a paper from one of the collaborations. Here's a famous plot in there. The thing I want to draw your attention to, so this is the mass of the Higgs, searching for the Higgs. This green area says theoretically inaccessible. And in the paper it says this maximum theoretically allowed value of Higgs mass is 85 GeV. So they just don't look there. They just stop looking. And as an experimentalist, this part is just crazy, right? I mean, this plot right here is basically a notion of sensitivity, and then so there's still some sensitivity there, and they just chop it off. And so whose fault is this, right? What is the lesson learned here? Is the lesson learned, which was expressed by several experimentalists, that this was bad advice, we should stop listening to theorists? That's not really the lesson that I took from this. The real lesson was that people were only considering the most simple versions of supersymmetry. There were lots of people saying, oh, there are these other more complicated versions of supersymmetry, you should look for them too. But it was actually the experimentalists that were saying, no, those are too crazy, blah, blah, it's too mathy, it's not real, etc. But even though we had sensitivity to look, we just didn't look. So that was really a sin of the experimentalists, kind of buying into the narrative of a little bit of math is good, but I don't know. So the lesson I say is that really that we should be testing more theories. And if you go back to this kind of zoo of possibilities, the problem we had was, how are we going to test all these ideas? It's not that we were being overly biased by the theory telling us only go look for this one thing. It's that we were overwhelmed by problems, and we didn't have a technique for being able to test them so well. So we did go back to some old data, which was nice. And we looked for the Higgs, and we had this opportunity to actually discover the Higgs in 10-year-old data while the LHC was being fixed. Needless to say, it wasn't in the data. We did not discover the Higgs. But it did motivate this whole kind of change in approach that kind of reframes the relationship between the theoretical community and the experimental community in particle physics. And that's the idea that kind of let the experimentalists be the empiricists that are collecting data and trying to characterize the devices that we're using to make measurements, and let the theorists come up with lots of crazy ideas and models, and let's build a service that's going to more efficiently allow theorists to be able to test those models without having to like convince some experimentalist to get their graduate student to spend 4 years to test that theory or something like that. And so this is something that's is ongoing, but again, it kind of reframes the relationship between theory and experiment. Okay, so now I'm going to kind of zip through a little bit more. So chronologically, the LHC gets fixed. We start collecting data. We start seeing collisions that look like this. Here's 4 red particles. These are muons flying out of the detector. This is the kind of thing we expected to see if we were producing a Higgs boson, so people were very excited. When we first turned on the LHC, we were not seeing evidence of supersymmetry or something, so we had to be patient and wait longer, but we did see evidence of the Higgs. This is the data emerging, and you see this little bump. This is one way of looking for the Higgs. This is a different way of looking for the Higgs. There's another bump, and the locations of these 2 bumps coincide at 125 GeV, which is the mass of the Higgs. So this was great, so discovery. Now, in some sense, this is a triumph of theory because, in the 60s, there was the idea that this particle should be there and we should build this gargantuan experiment. When you actually go to do the discovery, theory is not actually all that important in this plot. We basically fit this smooth curve to a polynomial, okay? And so it's also kind of interesting because there's sort of a bait and switch going on between, quantum field theory and all of this, and just a polynomial. In the end, that's kind of really the thing that we're testing. Is it a polynomial only or a polynomial with a bump on it? So it's very low brow at that point. But the role of theory, of course, was very important in guiding the design of the experiment and setting what the requirements were. And we would not have built this experiment and done this if it weren't for the theoretical guidance. So of course, that led to the Nobel Prize. And here's another example that happened just a few years later. This is even in the same this is the same plot that we used to discover the Higgs. Like over here to the left a little bit is the Higgs bump, and there's another bump. And people started getting excited. And in fact, after we put this out, there were hundreds and hundreds of papers by the theoretical community about this bump, because theorists are also, they're not that they don't care about experiment, they're thirsty and starving for some hint from experiment. So this was very exciting. But with more, people weren't really sure what to make of it, and it really revealed something that in the community, some people either thought this was very interesting, and some people thought, nothing of it. And why is that? It's because, subconsciously, we're basically doing what statisticians would call Bayesian data analysis. And so what we're wanting to say is there's a probability of a theory given the data. And that's what's happening is it's related to the probability that we would get that data from that theory times what's called a prior probability for the theory. And essentially for the Higgs, the prior probability was large because everyone is expecting that the Higgs would be there. So when we saw that bump, which is the green part, everyone believed it. But for the same size bump for some new thing that no one was expecting, this red number, the prior probability on the theory was small, so people weren't really believing that. And maybe that wasn't so bad because with more data, that bump went away. Okay, so now what's funny is that in this very short time between the discovery of the Higgs, there's been a lot of pessimism and a lot of back reaction against the sort of interaction between theory and experiment and sort of, what have you done for me lately attitude. And the answer for that is sort of bupkis, basically, is that we have been looking for all of these different things and we have not seen anything else. So all of these exciting things like extra dimensions, supersymmetry, technicolor, black holes, things like this, we have not seen evidence for any of that. And so there are a lot of people that feel like, we were led astray or something like that. There's also this was driving a lot of the discussion was we're kind of at a fork in the road, and for a long time the narrative was largely around naturalness, and with supersymmetry is the one example I described, and now maybe naturalness is not true, and we need some other principle, and like the multiverse is one of the driving principles that might explain this kind of direction, but there are other ones. So it's also interesting, a lot of people really hate this idea of the multiverse and this whole discussion and think that naturalness was like a con. And I think what we have to remember is that the community as a whole bought into this story, And it seemed very compelling. And the fact that nature is not working that way, that means that we're learning something very deep, right? I mean, our understanding of nature is changing quite a bit with this fork in the road, and we don't know how it's going to end. So I'm going to put it like in a slightly more mathematical footing, is that if this box is sort of the space of different theories that you could have, you could imagine two different types of experiments that you could do, the orange one and the green one. And the orange one, say, is sensitive to this region of the parameter space for the theory, and the green one is sensitive to this other region of the theory. And you have to decide which experiment do you want to build, okay? How are you going to do that? We don't have infinite resources. If we had infinite resources, you would just say all experiments are useful, we should just go measure everything. That's a very easy privileged point to take. In reality, we have limited funds, we have limited time on Earth, and what are we going to do? This is also true for theorists trying to decide what they're going to put their time into. Are you going to study string theory or something else, right? So, so if you just think about it, though, the ingredients that you need to answer this question about how to make this decision, there's two parts. The first part is that you need to have a model for the probability of the data given the theory. And this is what theoretical physics provides you. And no one's arguing about this. This is like objective, the part that everyone agrees the theory has consequences, and these are the consequences. You also need some notion of utility about like what it means, how valuable is it to learn something, or what do you mean by learning something about nature, or maybe you have a global climate change and you would rather try to solve that, or you have some sort of utility function that's telling you how you want to spend your time, right? But it turns out that to be able to answer this question in any kind of rational way, to decide it, you need what's called a prior on the parameter of the theory. You need to say the relative weight that you think before you do the experiment that this part of the parameter space is true or this part of the parameter space is true. And that's kind of obvious when you say it that way, but the interesting point is that that quantity is not something that comes from theory. That is not something you predict. There's no mathematical physics idea that's going to predict this prior on the space of the theories. And so really it's like an explicit form of bias. And this, if you go back to the empiricist rationalist debate, the thing that the empiricists are worried about is that this kind of theoretical bias is going to push you in the wrong direction, and confirmation bias and all these things. And bias has this very negative connotation among experimentalists. I mean, it sounds bad. I should avoid being biased, right? So this, I'll go back now to the kind of point of view of the data scientists and the statisticians, is that they think about these problems a lot. And so, for instance, one of the questions that you have, one of the fundamental trade-offs that you have is something called exploration versus exploitation. And this is not about Spanish conquistadors trying to decide what to do. This is about, for instance, do you want to continue doing the LHC experiments and exploit the statistical power that they provide to you, or do you want to stop doing that and spend your money to try to do something totally different? It's similar to the type of diversity that we're looking for in ideas between mathematics and physics. Do you want to explore more and more ideas, or do you want to try to go down that rabbit hole? And that's a fundamental trade-off. And then also, if you think about kind of theory on one side, data on the other, and this relationship between prediction and inference, if you go to study that, there are some very nice theorems that are called no free lunch theorems, NFL, and one of the aspects of the no free lunch theorems is it basically says if you don't assume anything, there is no decision rule, there is no strategy that's going to be generally better than another one. They're all on average equal. And so if you do well for some situations, you're going to do bad for other situations, and there's no way that you can avoid that. And so one way that this no free lunch theorem manifests itself is in terms of a bias variance trade-off. So you're probably familiar, like the idea of accuracy and precision. For statisticians, you would refer to the bias, like, if you throw darts, these are unbiased and these are kind of biased over here. And then the notion of variance, which is how scattered they are. And so so all of the experimentalists seem to want to be no bias. I can't have any bias. I can't allow any bias. But there are a bunch of really nice examples that show that if you want to do that, you're not going to make it very far. And if you allow yourself a little bit of bias, then you can reduce the variance dramatically. And you will be able to use data much more efficiently, and you'll be able to navigate the world very efficiently. And that's what humans do all the time. Okay, so the reason that we've succeeded so much in understanding the world around us is because we're heavily biased. And so there's this term that is used a lot in deep learning called inductive bias. And what's interesting is totally outside of the realm of physics, the things that people are talking about a lot right now are the role of compositionality, the role of symmetry, the role of scale separation. These are all physics ideas, and they manifest in a totally different context when you're thinking about like cats and dog images or all sorts of different things. So it's sort of like this point that was made before that mathematics appears everywhere. These concepts also appear all over the place, not just in sort of studying the fundamental world. So the last little bit I'll say is that in terms of, this isn't so much a trade-off, but just a fundamental thing about doing science and physics in particular, is that the old adage that correlation is not causation. When you think about statistics and deep learning and machine learning and what can you do with the data in a purely empirical setting, it's really only able to do things with correlations. And what we're after as physicists is something deeper about causation. And so there's a very nice book by Judea Pearl called The Book of Why, and he introduces this ladder of causality. And the lowest rung on the ladder, okay, which is ironically at the top, is association. This is just basically correlations in the data. And what you would like to be able to, and so an example is, what's the expected lifespan of someone who's a vegetarian and does not smoke? It's just a quantitative number that you can estimate from data. But then you would like to ask higher level questions, like intervention type questions, like how would my life expectancy change if I became a vegetarian? I don't have that data, right? So I would like to answer that question. It's a what if question. So similarly, like I'd like to ask what would happen in my experiment if I smashed the protons together at twice the energy, right? Physicists can answer these kinds of questions. There's also the kind of imagining types of questions of what would my grandfather still be alive if he did not smoke? I can't do some intervention to answer this question because my grandfather has passed away, right? So these kinds of questions I think are a lot of what's going on with very highbrow theoretical physics is you're imagining toy universes. What would the universe be like if the cosmological constant were very different? What if there were, n equals 4 supersymmetry? So with that in mind, if we go back to, I was talking about the Large Hadron Collider and these kind of relatively puny energy scales, while things like, superstring theory and et cetera that people are ultimately interested in are, potentially much, much higher energies, and there's a huge gap between them. So what's my take on that? So the way I'm going to end on this is basically some sort of analogy between how I would discuss basic research. If I were to talk to an experimental physicist who's like super grounded and say like, how do you justify your work searching for the Higgs boson when it has no practical applications, right? The kinds of answers you would get where, okay, well, basic research is very important. First you have discoveries that might not have any practical application like the Higgs boson. There are other kinds of discoveries that might lead to R&D, and eventually they might lead to applied technology. And this is kind of a story that you can tell for people that are only interested in applied technology. So what's the analog on the physical mathematics or mathematical physics side? And I think, roughly, this is a loose analogy, is that up here you have theories that don't describe our universe. All sorts of things that are very mathematical, toy examples, that in some sense are real in the context of mathematical physics. These are real idealized universes that mathematically exist, right? Then there are kinds of theories that may describe our universe, which are sort of like R&D. We don't know yet if they're going to be useful in describing our universe, but we're playing around with them and hope they might be able to. And then eventually there's like really applied technology, like the Standard Model really describes our universe, and then there are all sorts of effective theories and things like this. So of course we appreciate that these all feed off of each other, and it's very healthy to have basic research. And I think for the same rationale, I think it's very important that we allow ourselves to go down the road of basically pure physical mathematics, even if it doesn't describe our real universe. And with that, I'll end. Thank you very much.